Hey there, it's Shannon MATHCHICK Myers, and today we're going to take a look at alternating series. So let's warm it up by using some of our earlier skills to determine whether the series converges or diverges. So here we go. I'm looking at this one, and I'm thinking to myself that we could make this look like a geometric series. So if we rewrote this as the summation, as in goes from 1 to infinity, of -1 to the n, over 2 to the n times 2 to the 1, you see that's it, like n plus 1, then that in turn will be the summation as n goes from 1 to infinity of 1/2 times -1/2 to the n. So you can put this -1 to the n and the 2 to the n as -1/2 to the n. Groovy? Okay, so now looking at that, and we can just use the definition of geometric series, right? So, actually you don't need to go through all the steps since it turned into a geometric series. Convergent geometric series with absolute R equal to absolute -1/2 and 0 is less than absolute -1/2, which is less than 1. Cool? So, no comparison, no nothing, just a straight up geometric series with a little bit of algebra. Groovy? Okay, so here we go. The alternating series test. If we let a sub n be greater than 0, the alternating series summation n equals 1 to infinity of -1 to the n times a sub n, and the summation n equals 1 to infinity -1 to the n plus 1 times a sub n converge when both conditions below are met. And so the limit as n approaches infinity of a sub n has to be equal to 0, and a sub n plus 1 needs to be less than or equal to a sub n for all n. Okay? So the second condition, of course, can be modified to require that 0 is less than a sub n plus 1 is less than or equal to a sub n for all n greater than some integer capital N. Now, one of the trickiest things about the alternating series test is when that first condition fails, what happens is it diverges by the nth term test for divergence. We'll run into that in one of our problems, and I'll point it out. Okay? All right, so let's look at this first one. Determine the convergence or divergence of the series and explain. So let's do this. It's an alternating series, so step 1, what test will we use? We'll use the alternating series test. Which, if you want, you can just call the AST. 2. Step 2, conditions. Here, you just identify your a sub n. So you take out the negative portion, the alternating portion, and we would just get 1 over 2 to the n plus 1, and that is greater than 0 for n greater than or equal to 1. So conditions check out. Step 3, we'll run the test. So the first part of the test is finding the limit as n approaches infinity of a sub n, which we said was 1 over 2 to the n plus 1, which of course is 0, so that one checks out. Now the second one is a sub n plus 1 less than or equal to a sub n. Well, let's check it out. A2 is going to equal to 1 over 2 cubed, which is 1/8. A1 is going to equal to 1 over 2 squared, which is 1/4, and 1/8 is certainly less than or equal to 1/4. And then, let's see, A3 will equal to 1 over 2 to the 4th, which is 1/16, and that's less than or equal to 1/8, which we already found to be A2. And do you see it'll continue? A4 will be 1 over 2 to the 5th, which is 32, which will be less than or equal to 1/16, which was our A3. So that'll continue, and so this checks out. And so, step 4, conclusion. The summation, as n goes from 1 to infinity, of -1 to the n over 2 raised to the n plus 1 converges by the alternating series test. Groovy? All right, I like the alternating series test, actually. All right, let's look at our next example. So now we have -1 raised to the n over the natural log at n plus 1. So, step 1, I'm going to pick the test as the alternating series test because we have an alternating series. And then, conditions. Which is our step 2, sorry. Step 2, conditions. Well, taking out the alternating part, we'll have 1 over the natural log at n plus 1. And that is greater than 0 for n greater than or equal to 1. All right, so step 3, run the test. So part 1, the limit as n approaches infinity of 1 over natural log at n plus 1 is equal to 0. So that checks. Because remember, the natural log function increases without bound. And then 2, if we use a little bit of reasoning, since the denominator, natural log at n plus 1, is increasing, and the numerator is constant, so it's not going to change anything up or confuse anything, is constant and positive, one over natural log at n plus 1 is decreasing. So a sub n plus 1 will be less than or equal to a sub n. So if you wanted, you could break your calculator out and compare term by term, but I didn't feel like using the calculator yet. All right, so that checks. So step 4, our conclusion. And I know it might seem a bit much to have these steps, but you know what? If you have these steps, it's going to help you stay on track, and it's going to help you learn the tests, right? The worst thing that you can do, is, especially if your work is on, like, say, WebAssign or some online platform, your homework, the worst thing you can do is just guess and say, oh, it's going to converge or diverge. I have a 50-50 chance, because most instructors will not test like that. And if you're in my class, I certainly do not. I have you show these steps. Okay, so the summation as n goes from 1 to infinity of negative 1 to the n over natural log at n plus 1 converges by the alternating series test. Cool, cool? Excellent. All right. So here we go. We have this guy here, maybe a little complicated. So step 1, what's our test? Alternating series. You know, when you learn the ratio in the root test, you may want to, you know, move away from alternating series, but always think about this test for whenever you have an alternating series. Think about it as a potential. Step 2, conditions. All right, so take away the alternating part. Our a sub n is equal to n squared over n squared plus 4, which is greater than 0 for n greater than or equal to 1. Okay? So, step 3, run the test. Maybe I'll do it up here. 3. Run the test. So, first off, let's see what we get. The limit as n approaches infinity of n squared over n squared plus 4. Well, I am going to divide by that highest term in the denominator, highest power of n, to get it in the shape where we can find the limit. So we'll have 1 over 1 plus 4 over n squared. And that limit is going to be 1 over 1 plus 0, which is 1. Now this is equal to 1, which is finite and positive, right? So basically, we can go straight to our conclusion And we're going to find out that this summation, as n goes from 1 to infinity, of -1 to the n plus 1 times n squared over n squared plus 4 diverges not by the alternating series test, but by the nth term test for divergence. So basically, if the conditions are met and you get something that's non-zero, and actually I think it just needs to be, you know what, my bad here, let me cross this out. I'm thinking of the limit comparison test, which is not equal to 0. So if you get something that's non-zero, it diverges by the nth term test for divergence. Cool, cool? Okay. So let's take a look at part D. Part D is one of those where we're probably going to want to expand it out a little. So this is going to equal to 1 over 1 times cosine of 1 times pi plus 1 over 2 times cosine of 2 pi plus 1 over 3 times cosine at 3 pi. You're starting to see the trend. And then plus 1 over 4 cosine of 4 pi plus dot dot dot. So this is a real sneaky way, that using the sine and the cosine can be a sneaky way to make an alternating series. So this one would be cosine pi, which is just -1, right? And then we'll have plus 1/2 cosine 2 pi is 1. So -1 plus 1/2. Cosine 3 pi goes back to -1, so we'll have -1/3, and then plus 1/4, minus plus dot dot dot. It goes on like that. And so this is equivalent to the summation as n goes from 1 to infinity. Notice that on the on the odd terms you've got a negative, and on the even terms you've got a positive. So our -1 will just be to the n, and then we have over n. And now we don't have to worry about that cosine business because we figured out its pattern. Groovy, right? So here we go. Step 1, what test will we use? Well, I say we use the alternating series test. And then step 2, conditions. A sub n is equal to 1 over n, which is positive for n greater than or equal to 1. And then step 3, let's run our test. So, first part, the limit as n approaches infinity of 1 over n equals 0, so that checks out. And then the second part, comparing successive terms, they need to be less. So is a sub n plus 1 less than or equal to a sub n? Let's check it out. A2 equals 1/2. A1 equals 1 over 1, which is 1, so it's certainly 1/2 is less than or equal to 1. A3 will be 1/3, which is less than or equal to 1/2, which was our A2. And it will trend like this. I'll do one more line. A4 is 1/4, which is less than or equal to 1/3, which was A3, dot, dot, dot. Cool, cool? So we would say yes. And then step 4, conclusion. The summation as n goes from 1 to infinity of -1 to the n over n, which equals the summation as n goes from 1 to infinity of, this is where it had 1 over n times cosine at n pi, converges by the alternating series test. Cool, cool? All right, next up, here we go. You can use the alternating series remainder to approximate the sum of an alternating series. So if a convergent alternating series satisfies the condition a sub n plus 1 less than or equal to a sub n, then the absolute value of the remainder, now let's call that R sub capital N, involved in approximating the sum S by S sub n is, and S sub n is like the capital Nth partial sum, right? Is less than or equal to the first neglected term. So the first term that you don't add. So basically you've got this situation. Absolute S minus S sub capital N is equal to absolute R sub n, which is less than or equal to a sub n plus 1, which is our first neglected term. All right, so what we're going to do for these, just as a time saver, is we're going to assume these series converge. If you want to, for fun, you can run the test, but I checked them and they do converge. So here we go. What we'll do is we'll take a look at approximating our sum. So they want us to use the first 6 terms, right? So S sub 6 would be equal to -1 to the 1 plus 1 over, and then times 1 over 3 to the 1 plus -1 to the 2 plus 1 times 2 over 3 squared plus -1 to the 3 plus 1 times 3 over 3 cubed plus -1 to the 4 plus 1 times 4 over 3 to the 4th plus -1 to the 5 plus 1 times 5 over 3 to the 5th, and then the 6th term would be -1 to the 6 plus 1 times 6 over 3 to the 6th. So I just plugged in wherever there was an n, I plugged in which one we were on. So this is A1, this is A2, A3, A4, A5, and A6. And let's simplify that a bit. So we'll have S6 is equal to, so we'll have -1 squared, so that'll turn that positive, so we'll have 1/3. And then -1 cubed means we'll have a minus, and then we'll have -2/9. and then we'll have another positive, and then we'll get 3 over 27, and then a negative will be 4 over 81, positive again, 5 over 243, and then a negative, and we'll have 6 over 729. That's 3 to the 6. Okay, so now you can use your calculator to do this. You can also write in the summation if you want. It probably takes about an equal amount of time. I'll go ahead and do that. If you go to second 0, you'll get to catalog, and we want to sum. We're summing a sequence, so you go back to catalog, and you go to the sequence that has the parenthesis, and then you put in your expression, so that's going to be parentheses, another parenthesis, be careful, and then we'll have -1 raised to the, I'm going to put K's in just to be more proper, so alpha K, and then it's K plus 1, and then times K, and the numerator parenthesis, and then divided by 3 raised to the K. So we've put in our expression. Next goes the variable that we're using, which is K. And then we're going from 1 to 6, and the change in K, or whatever, will be 1. And that gives us an approximate value. We can also get, we should be able to get the actual value of 5/27. So S6 equals 5/27. Good so far? Okay, so now let's kind of get a feel for what all we need, remember? So we're looking for approximating the sum. So we're going to use the first absolute value for this problem. So we're going to use this business, absolute S minus S6 is less than or equal to A sub 6 plus 1, because our n is 6. So absolute S minus S6 is going to be less than or equal to A7. So we need to find A7. So A7 is going to be -1 to the 7 plus 1 times 7 over 3 to the 7th. So that'll end up being positive, and then we'll get 7. If you times 729 by 3, you get 2187. Cool so far? So we're going to use this information in this inequality. So S minus 5/27, that's in the absolute value, is less than or equal to 7 over 2187 So here we go. This is just from, we found S6 to be 5/27. We found A7 to be 7 over 2187. Now, using properties of inequalities, we can take those absolute value jail bars off, right? If we have negative 7 over 2187 is less than or equal to s minus 5/27, which is less than or equal to 7 over 2187, just by definition of an inequality, absolute value inequality. And now if we add 5/27 to each part of the inequality, we will get, let's grab the calculator. So we have 5/27, and I'm going to say minus 7 over 2187. And then I'm going to get that as a fraction again. Oops. Going to math, fraction, enter. So that's 398 over 2187. And then that will be less than or equal to our sum, whatever, and that's less than or equal to, so I'm going to go second entry, or actually second answer, nah, I'll just type it in, I'm being lazy. So now 7 over 2187, and then minus 5, plus 5 over 27, and getting that in a fraction. No, it needs second, we need math, fraction. Enter, we get 412 over 2187. And so using 6 terms, our sum is going to be somewhere in between these values. So we did get those fractions. So if you went, so this would be like exact, approximate would be, our first one was what? 0.18198, I'll go 5, I guess. Less than or equal to s, less than or equal to 0.18839. Cool? All right, so we got that going on. So that was a situation where we knew how many, we were given how many terms we wanted to use. And we had to find out the interval interval for that sum. Now, next problem, determine the number of terms required to approximate the sum. So for this one, we're going to be using absolute R sub n. And we know that that's going to be less than or equal to a sub n plus 1. And they've given us a sub n plus 1 to be 0.001. And just to make it easy, I'm going to write it as a fraction, 1/1000th. Cool so far? Absolute value, of a sub 1 is equal to absolute negative 1 to the 1 over 2 times 1 factorial, which is equal to 1 over 2 factorial, which is just 1/2. which is not less than or equal to 1/1000th. All right, so that would be too big of a margin, right, if we just used that amount. Absolute A2 is equal to absolute -1 squared over 2 times 2 factorial, which will be 1/4 factorial, which is 1/24, which, let's see, is that less than 1/1000? No. So, continuing, absolute A3 is equal to absolute -1 cubed over 2 times 3 factorial. That will be 1/6 factorial, which is good, 1/720. And that is still not less than or equal to 1/1000. I think this next term will be fine. Absolute A4 will be -1 to the 4th over 2 times 4 factorial. The negative goes away, and the absolute value will get 1/8 factorial, which is 1/, let's see, let's find our 8 factorial. Plug in 8, math, probability, factorial, enter. That's 40,320, and that is definitely less than or equal to 1/1000. Cool, cool. So basically, the remainder, when we add, if A4, right, was the first neglected term, so that if this was the first neglected term, then we would be within that 1/1000 bound. Cool. So what does that mean? That means that 3 terms are needed to approximate the sum with an error less than or equal to 1/1000th. Cool, cool? So, A1, A2, and A3, if you use those 3 in the sum, then you'll have your bound would be less than or equal to actually 1/40,320. Cool, cool? All right. All right, absolute convergence. So if the series summation absolute A sub n converges, then the series summation A sub n also converges. So that's kind of powerful, because if you look at the absolute value of your series and it converges, then you've got basically absolute convergence. So the series summation A sub n is absolutely convergent when the summation absolute A sub n converges. And we'll be using that. That's why it's so nice to use the ratio or root test, because if you get convergence, you get absolute convergence, and we'll be learning that next time. The series summation A sub n is conditionally convergent when the summation A sub n converges, but the summation absolute A sub n diverges. Cool? Okay. So, and in here, a sub n doesn't, it can be negative. So don't think about this as the condition for the the a sub n that you use for that alternating series test. Okay, how it works. Let's, well, you've got to figure out if it converges, right? So there's a couple of ways to go about this. I mean, I think that if you believe that the given series is going to diverge, then I would just work with your given series first. I mean, there's oftentimes what's going to happen is you might have to do both. All right, you might have to do two tests. So I'm thinking, because the denominator is going to grow really quickly. So I think that this alternating series is going to converge. And so because of that, I am going to look at the absolute value of it, because if the summation of the absolute value of my sequence converges, then the summation of the sequence without the absolute value will also converge. So I'm gonna hope I get convergence with the absolute value. So we're gonna look at the summation as n goes from 0 to infinity of absolute -1 to the n over e to the n squared. Well, what that's going to take away is the alternating part, right? So this will just be, the e will always be positive, so we'll have 1 over e to the n squared. That's what I'm going to work with. And we'll keep our fingers crossed that it converges, and then we just need to do one test. So step 1, what test should we use? We've taken away the alternating portion of it, so we can't use alternating series. Now, I think this is going to converge, so we would basically need a bigger series that converged to use a direct comparison test. So I think I'll use a direct comparison test. And limit comparison tests might be good too. So I'm going to use the direct comparison test. And the conditions. So when I look at the sequence inside, I'm thinking geometric, right? So since I am thinking this will be convergent, my a sub n is going to be the sequence that I'm starting with, right? Which is 1 over e to the n squared. That is positive. And my b sub n is just going to be 1 over e, which is going to be larger term by term. If I go 1 over e raised to the n, I'll end up with e to the n instead of e to the n squared. And so that's going to end up being larger term by term, which is what we wanted. Step 3, run the test. A1, or actually it starts with 0, so A0 equals, remember we're using 1 over e to the n squared, so we would just get 1 over 1, B0 would be equal to 1 as well, so that fits so far, it's equal to. Alright, so now A1 is going to be 1 over e, and B1 is also going to be 1 over e. So again, they're equal. Now let's see what happens. A2 is going to be 1 over e to the 4th. But over here, This one will just be 1 over e squared, which is larger. So we're in a good space here, and let's do one more. A3 will be 1 over e to the 9th, right? Yep, 3 squared is 9, as opposed to 1 over e cubed. So we're good here. That'll continue on. So that means that 0 is less than a sub n, which is less than or equal to b sub n for all n greater than or equal to 0, actually. Now, we also need to talk about the comparison test. So the summation from n equals 0 to infinity of 1 over e to the n is a convergent geometric series. Absolute r equals absolute 1 over e, and 0 is less than absolute 1 over e, which is less than 1. If you want to double check, you can always go to your calculator. 1 divided by e to the 1 is 0.3678, so we're good. And for our conclusion, the summation as n goes from 0 to infinity of, we did the absolute value, remember? So I'm actually going to write it like that again, of the absolute value of negative 1 to the n over e to the n squared. And what did it say? It's absolutely convergent because this one the absolute value converge. So we don't have to do any more tests on this one. Convergent, and we use the direct comparison test for the test, and then the absolutely convergentness would be definition. Cool? All right, so now let's look at one more of those. So for this one, I think this is going to diverge. So since I think this is going to diverge, I'm seeing that arctangent in, I'm just thinking it's going to diverge. So I'm going to use the alternating series test on this one. So here we go. Step 1. What's our test? The alternating series test. Step 2. Conditions. A sub n is equal to arctangent at n. Now remember, the arctangent, once you go to the right of 0, then your outputs are all positive. So this is greater than 0 for n greater than or equal to 1. And then step 3, Run the test. So, part 1, the limit as n approaches infinity of arctangent at n equals, awesome, pi over 2, which is not equal to 0. So what's our conclusion on this? So it fails that condition, but by the nth term test for divergence, the summation as n goes from 1 to infinity of -1 to the n plus 1 times arctangent at n diverges. And you're done. If you like what I'm doing, hey, go ahead and click on that subscribe button, like the video, share the video, and I'll see you next time. Bye.